factor. And that's what we just used over here. What we say is, if m dx plus n dy is not equals 0, is not exact, make it exact. What does that mean? Find a function u of x and y such that when I multiply, or divide, makes no difference, both sides of this equation by it, the new equation, which you see has the same solution set as this one. See, in other words, something is a solution of this equation if and only if it's a solution of this equation. See, it's equals multiplied by equals are equal. What if this is exact? See, that's precisely what we did up here. Y dx minus x dy was not exact. The u of x, y in that case was just 1 over y squared. We multiplied both sides of the equation by 1 over y squared and made this exact. The problem is this, though. It turns out, theoretically, that if an equation of first order, first degree is not exact, there is an integrating factor. In other words, something that you can multiply it by to make it exact. The problem is that in real life, that factor is harder to find than the solution of the original equation in most cases. Namely, how would I find a u such that this was exact? Remember, the condition for exactness is that the partial of this with respect to y has to equal the partial of this with respect to x. Remembering that u is a function of x and y, I have to use the product rule over here. I get u times the partial of m with respect to y plus the partial of u with respect to y times m equals u times the partial of n with respect to x plus the partial of u with respect to x times n. And look at this equation. I'm trying to solve this for u, and notice that this is still a differential equation, but it involves even partial derivatives. In other words, to solve this equation involves having to solve a partial differential equation, which is even harder to do than the equation that we're trying to solve now. Well, at any rate, let me show you now, in summary, why people refer to differential equations as a cookbook course. Philosophically, there's nothing to solve.